Thank you for the introduction, Sojin. Hi, everyone. Thanks for coming to this talk. I'm Anne, and today I will be sharing with you our work, Starfish, a topology routing co-design for small-scale data centers. This is a joint work with Vipul from Conviva, Sangeetha from UC Irvine, my advisor, Maria, and Brighten from UIUC. Now, leaf-spine has always been the default topology for small-scale data centers. But in this work, we show that without adding any hardware, without increasing bandwidth, just by rearranging the existing networking equipment, we can improve performance by up to 56%. And this is purely an effect from using a well-chosen topology with a well-designed routing. So really, leaf-spine, the default for small-scale data centers today, is suboptimal. Now, you might be wondering, how often does this actually matter? Well, as it turns out, small-scale data centers are everywhere. Uptime Institute conducted a survey on global data centers in 2024. And the survey shows that at least 45% of all enterprise IT workloads are run in small-scale data centers. This points directly to their prevalence and importance. Also, these on-premise data centers is just one category of small-scale data centers. Besides the enterprise private data centers, they are also prevalent in edge clouds, internet exchange points, and others. And by small-scale data centers, we are referring to those that use tens to a few hundred racks and hundreds to a few thousand servers. However, existing literature has disproportionately looked at hyperscalers, which cannot be directly transferred to small scale. And none of the existing literature looks directly at these small-scale data centers. And this is the gap that our work is trying to target. Here is an outline for the talk today. We have already discussed the importance and prevalence of improving performance for small-scale data centers. Next, let's take a look at why this can be challenging. Now, from the perspective of a small-scale data center operator, what do we actually want? One thing is that we want to practically get the most performance out of our network while staying failure resilient. And more specifically, there are two decisions to make here. One, how should I connect the servers and switches I have? So this is topology. And two, for each flow, which path should it take? And thus, what entries should I install on switches? So this is routing. These two decisions are linked to each other. A topology can expose more paths and additional capacity, but without deployable routing, these additional paths and capacity are just not usable in practice. More concretely, the operator has three requirements in mind. The first is performance. So we want to have high throughput and low latency under both uniform and skewed traffic. The second is fault tolerance, which means that the network should retain its high performance under random link and switch failures. The third is deployability. The design should support practical routing and should be easy to wire and manage. Now, the challenge is that existing work usually do well in some of these dimensions, but not all three at the same time. Let's take FAT-tree as an example. FAT-tree is simple, well understood, and widely deployed. However, failures of aggregation or call switches can remove many available paths for many rack pairs, thus degrading its performance unevenly. Now, the performance of FAT-tree also comes with costs. So cross-port traffic takes longer path. Cross-port traffic takes longer path, which increases the bandwidth tax. Or in other words, now more network resources are consumed for each unit of delivered data. And because FAT3 is an indirect topology, many ports must be reserved for fabric connectivity to keep the network unoversubscribed. Under a fixed budget, however, we have to either support fewer servers or attach more servers, but have to be oversubscribed. At a small scale, however, operators often choose two-layer leaf-spine instead, which indeed has shorter paths, but they suffer from the same oversubscription trade-off. Similarly, Dragonfly is very popular in high-performance computing, but its intergroup global links are prone to congestion and failures. And more recent expander-based proposals are great with performance, but suffer from deployability issues, such as wiring difficulties and a lack of practical routing scheme that do not require special hardware or special protocols. So now we've looked at the challenge of achieving the three requirements simultaneously. Let's move on to see how Starfish handles this challenge. While it is indeed difficult to achieve all three simultaneously and resolve this trilemma, the small scale has its own distinct design space and sees an opportunity of path length headroom. Specifically, paths are naturally shorter at the small scale. And this means that we could afford design choices that improve fault tolerance and deployability without paying a significant latency cost. And this is what allows us to sidestep the trilemma at the small scale. More specifically, Starfish co-designs topology and routing for small-scale data centers. And let's look at our topology design first. This is the topology Starfish uses. We call it D-ring due to its double ring. And D-ring is organized around a two-level structure. At the top level, we define a supergraph where supernode I is connected to supernodes I+1 and I+2 mod n. Now, each supernode in the supergraph is actually a group of racks. And every pair of tall switches lying in adjacent supernodes has a direct link. Now, if I flatten the two-level structure of D-ring and draw out everything, this is what a D-ring with 8 supernodes and 3 racks per supernode looks like. D-ring achieved performance, fault tolerance, and deployability simultaneously. So what's the magic behind D-ring? First, D-ring is direct, meaning servers are distributed across all switches instead of just a subset of them. This helps with smaller rack oversubscription and thus higher performance, where traffic is skewed and the major bottleneck is rack ingress and egress. Next, the superlinks and the double ring exposes many near shortest paths. This is crucial for achieving high performance under more skewed traffic, where the major bottleneck is under more uniform traffic, where the major bottleneck is fabric capacity. And this is also crucial for fault tolerance. And lastly, D-ring organizes its racks into natural units of co-placement and packaging. And this block-based design makes the cabling layout cleaner and allows links from a block to be bundled and neatly routed to another block, helping manageability. OK, now we've discussed the topology. As I mentioned before, routing is also a crucial piece here. A topology can expose many paths and higher capacity, but we need practical routing to actually leverage those paths and the higher capacity in practice. So how does Starfish route? One may ask, is it sufficient to just use the shortest path? To answer this, let's take this pair of source and destination as an example. Since they are directly connected, there is only one shortest path of length 1 between them, which can be very congested if servers in these two racks have large volume to send. Now, how about using this path then? We could potentially have many paths like this one. But this path is also not ideal, because it's really long and incurs high bandwidth tax. So in short, the paths used by rack pairs need to balance path length and path diversity. To put it in practical terms, it means that we should use near shortest path only when needed. Starfish's routing effectively balances path length and diversity by leveraging a structural property in D-ring. For a given source-destination pair, the number of the shortest paths is proportional to the number of hops for these paths. So put more simply, the shortest path length. We have a more rigorous framing in our paper, but I will just give a quick intuition here. So for this pair of source and destination 1, it has one shortest path of length 1. But now for this pair of source and destination 2, the shortest path is of length 2, and there are 6 of them. Starfish's routing leverages this property by designing a novel path selection scheme called shortest in K. In shortest in K, we use all paths from source to destination, which are either the shortest paths or path of length smaller than or equal to K. Let's do an example here. Say today we set K to 2. For this pair of source and destination 2, the shortest path is already of length 2, and there are a good number of them. So nothing will change for this pair. We just use their shortest path. But today, for this pair of source and destination 1, the shortest path is of length 1. And there is only one path. So we also want to make use of the length 2 path here, which would add these 6 paths, ensuring that we have diverse paths for this pair too, but we also constrain the path length. One thing worth highlighting here is that shortest in K can be run on standard hardware via VRFs. On the right, I will explain the general design for a generic K, and on the left, I will run an example with K equals to 2. So each physical router will be partitioned into K virtual routers. And let's say today there is a link going from R1 to R2. And we create the following virtual connections in the VRF graph. The cool thing here is that we just need to run shortest path routing on this VRF graph. And we have a prototype with BGP implemented in Genus 3 simulator, and we also provide a correctness proof in the paper. Now, routing involves 2 parts. One, which path to use for a source destination pair, and 2, how to divide traffic across the available path. We do path selection based on shortest in K, and next I will introduce our weight assignment schemes. So Starfish supports 2 modes of weight assignment depending on what's available. Oblivious weight assignment is easy, where traffic is simply split equally across all available paths. And the second mode is semi-oblivious routing, where a central controller collects traffic from the torus, solves a multi-commodity flow-based linear program, and then distributes the weights back to the torus. I will not go into details here, but I will just share 2 insights. First, we observe that good path selection schemes facilitate further weight optimization. And second, distributing traffic more widely accommodates traffic variations over time. Now that we've gone through the design, let's see how Starfish actually performs. In our paper, we demonstrate the following key takeaways. Starfish effectively supports more capacity on real-world traces. Starfish is resilient to random link and Tor failures. And Starfish's performance benefits are more pronounced at small scales and with larger oversubscription. And in the interest of time, I will just show a subset of the results here. And the results we are going to show are all based on an HT-sim packet-level simulation. First, we show that Starfish effectively supports more network capacity on real-world traces. So we use data from a university data center and a private enterprise data center released by prior work. We measure by injecting increasing amount of traffic into the network and measuring the tail latency. We use the same number of switches, servers, and links for all networks that we compare. So naturally, with more traffic, tail latency would increase. But when this curve is further to the right, it means that the network can effectively support more capacity. First, on a D-ring topology, Starfish's routing supports 26% more traffic on average than VLB, which is the strongest routing baseline. And next, we also compare Starfish with other topology routing code designs. So leaf spine is used with ECMP, and it is the status quo today. Here, Starfish supports 56% more traffic on average than leaf spine. And Starfish Oblivious also supports 33% more traffic on average than leaf spine. And these numbers here show the huge potential that small-scale data centers can gain just by rearranging their existing networking equipment. Also, note here that Jellyfish does not come with a routing scheme that can be implemented with off-the-shelf hardware and standard protocols. So here, we use Starfish's routing for Jellyfish. And you can already see that it performs really well. In fact, Starfish's routing enables Jellyfish to support 52% more traffic on average than leaf spine. And this is because, empirically, Jellyfish also satisfies the property needed for shortest linear K to perform well. And next, we show that Starfish is also resilient to random link failures. We compare Starfish with leaf spine and an oracle that knows the failures and thus optimizes routings with the failures in mind. I'm going to show the slowdown of tail latency when different percentages of links reduce their bandwidth to half. Here are the lines. We see that Starfish's slowdown is at worst 1.37, and it is really close to the oracle. In comparison, leaf spine sees larger and more varied slowdowns. Now, to conclude, Starfish enables small-scale data centers to support 56% more traffic just by rearranging their existing networking equipments. Starfish also enables Jellyfish topologies to support 52% more traffic than leaf spine with a ready-to-deploy routing scheme. We hope that the first step taken by our work would encourage future efforts from the community on small-scale data centers. And if you are operating a data center, if you are operating a small-scale data center yourself, I will be more than happy to chat. Our code is publicly available, and you can find out more about Starfish by scanning the QR codes here. And here are the image references, and thank you very much.